In today's video, let's see how to solve few example problems on bilinear transformation. What is bilinear transformation? Bilinear transformation is used in digital signal processing to transform continuous time systems to discrete time systems. Now let's get into our problem. Here on the screen you will be seeing a question in which we are asked to obtain the digital low pass filter from the given system function. From the question we can interpret the given cutoff frequency and sample frequency as 100 Hz and 1000 Hz simultaneously. Now we'll be obtaining the digital frequency omega c by using the formula 2 pi into fc by fs. Now by using bilinear transformation to obtain digital low pass filter, first we have to frequency wrap by using the formulas for different filters as shown in the table. For low pass, we'll be using the formula S is equal to S by omega c. To find the analog frequency omega c, we'll be using the formula omega c is equal to 2 by t tan omega c by 2. Thus, the obtained omega c 0.65 is used to denormalize the given system function in the question. So, by denormalizing the given system function, we'll be obtaining the system function in the analog time. So, now we'll be transforming the given system function to obtain the digital low pass filter system function. By using the bilinear transformation, now we'll be substituting S is equal to 2 into Z minus 1 by T into Z plus 1 in the denormalized transfer function system function obtained before. Thus by substituting we'll be getting the system function of the digital low pass filter. Here capital T represents the sampling period. Now, let's see how to obtain the high pass filter for the same given system function. The process till finding the analog frequencies is the same for the high pass filter as well. Now, for frequency wrapping, we'll be following this table for high pass filter where we have to substitute S is equal to omega c by S, whereas we have used S by omega c for the low pass filter. Whereas for band pass filter, we'll be using the different formulas as shown in the table. Now, after denormalizing h of s omega with s is equal to omega c by s, we'll be obtaining the denormalized system function for the digital high pass filter. Now, using bilinear transformation, we'll substitute s is equal to 2 into z minus 1 by t into z plus 1 to obtain the digital high pass filter system function. Thus, we'll be obtaining low pass filter and high pass filter using bilinear transformation from the given system function. Later, let's see the MATLAB implementation of these two system functions and see how the graphs varies with the frequency. Implementation of low pass filter, we'll be using the below given functions which are inbuilt in the MATLAB. The given below function b comma a is equal to butter of n comma omega c comma filter is represents the graph of a Butterworth filter with order n with cutoff frequency omega c and type of filter. So by using this function we'll be implementing in the MATLAB implementation of the low pass filter which we used in the above example. By by running the code in the MATLAB we'll be getting the graph as shown in the figure, and from the graph when you point the graph at the near the cutoff frequency we can observe the graph bending exactly at the cutoff frequency, which is exactly similar to the ideal low pass filter graph. Whereas coming to high pass filter, we will be replacing the type of filter from low to high in the statement as shown in the above. And after running the above code, we will be getting the graph as shown on the screen. In the same manner as shown in the low pass filter, where we point our cursor near the 0.65, that is the cutoff frequency of the filter which we have designed. We will be observing the bend of the curve, which is exactly similar to the graph of ideal high pass filters. Thus, we solve the transformation or design of the filters using bilinear transformation. Thank you.